And let us see and go deep into this subject with a topic called PN junction diode first. So this is a PN junction diode. You might have already learned what is this PN junction diode. This PN junction diode, it is a combination of P-type semiconductor and N-type semiconductor. So how this P-type and N-type semiconductor are formed means, first take a crystal, a silicon crystal. Take a silicon crystal. A silicon crystal is taken. A silicon crystal is taken, and to this silicon crystal or germanium crystal, P-type and N-type impurities are added. P-type impurities, what are P-type impurities? Already we have studied. The shortcut method is baggy, boron, aluminum, gallium and indium. And the N-type impurities are shortcut method is Fab, phosphorus, arsenic, antimony and bismuth. So add towards one side P-type impurities, this one, and add towards one side N-type impurities. So it will form like this. So this is a P-type where the majority charge carriers are electrons. Majority are electrons and minority are holes. Minority are holes. And this is formed N-type semiconductor where the majority charge carriers are, here minority charge carriers are electrons and majority charge carriers are holes. Here majority charge carriers are electrons and minority charge carriers are holes. Now you can see here all holes are positively charged particles, so therefore all are having positive sign, and all electrons are negatively charged particles, so therefore they are having a sign here. But here you need to represent here and study with respect to ions now. So here what happens is every plus here, every plus or every minus, if you consider here every minus it will donate an electron. It's nothing but an atom. This is an atom, and this will donate an electron. This minus donates an electron, which is called dot, and it will be converted to ion. So this one is called as donor ion. It will be converted to plus round. So plus round is called donor ion. Plus round is donor ion, and this dot is called electron. This dot is called electron. Likewise, complete structure, negative sign is being donated with electron, and therefore it will be converted to ion. Negative structure, electron. Negative structure, electron. Okay. Likewise, here the complete thing is given by ions and electrons. So here the complete thing is represented by ions and electrons. Here also come to this side. This is plus. Plus means the majority charge carriers are holes. So it will have a hole beside this, and this plus will be converted to minus round. So it will have a hole here. This plus will be having a hole, and it will be converted to ion. So this ion is called acceptor ion. And this is called as a hole. So likewise, so here complete plus will be having a hole nearby it, and it will be converted to ion. Hole by it, and it will be converted to ion. Hole by it, and it will be converted to ion. So this is actually the original structure of PN junction diode. PN junction, the original structure of PN junction, minus hole ion, minus round, it's an acceptor ion and a hole, right? So likewise, if you see here the nearby atoms, here this is called as a junction, as you already studied. A hole is there, junction, a hole is there, negative ion, hole. Here donor ion, electron. Now see here. The structure will be like this. The structure will be like this. This is acceptor ion, this is acceptor ion, and therefore the other thing is hole nearby it. This is called donor ion. This is called donor ion, and nearby thing is called electron. This electron is negatively charged particle. Okay, and this hole is positively charged particle. Please do remember. That's what a plus sign is kept over there. Okay. Now here, if this donor ion, if it is donating one electron here, and it will not be moved here, only electron will be moved here. That you need to remember here. And this acceptor ion, while it is having a hole here, this acceptor ion minus round will not move, and only this hole will move, right? Only that hole will move. Now see here, what happens here due to diffusion. First point is due to diffusion. Due to diffusion, what happens? Due to diffusion, these charge carriers, what happens due to diffusion, because all are positively charged particle here in p type. If all are positively charged particle, due to diffusion, what happens means they will collide with one another, and they will move from higher concentration to lower concentration. Where is lower concentration present? Lower concentration is present towards this side. So they will move from left side towards right side, right? Which will move means holes will move from left side to right side. Similarly, n-type semiconductor electrons, in n-type semiconductor majority charge carriers are electrons, so therefore more number of electrons are present here. So all these electrons moves from n-type to p-type because they are repelling with each other, this minus 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 signs, and therefore they are moving from right to left. They are moving from right to left. This is called diffusion. This is called diffusion, right? So diffusion of hole will move from p-type to n-type. Diffusion of electron will move from n-type to p-type. So while they are moving here, this hole and this electron will get recombined, and it will move. It will recombine. It will recombine, and it will die. It will expire. This plus and this minus, it will expire now. It will recombine, and then it will expire. See here, this is a structure where the nearby electron and hole are being recombined, and they have been expired. And they have been expired. And see here, the nearby atoms here, this minus and this plus is not expiring. This plus and this minus is not expiring. Why it is not expiring means, because this minus moves towards the junction here. Up to this point it will move, but it will not cross the junction because it is overcome by this negative charge. This is the negative charge, immobile negative charge. This is called immobile negative charge. Please do remember. This is called immobile negative charge. That is called immobile negative charge. It will not move. Immobile means it will not move. Immobile negative charge. And what about this one? This is called immobile positive charge. That is called immobile positive charge. Immobile positive charge, where it will not move from one point to another point. Only the electron and the hole, they have got recombined, and therefore they have been expired, and those charge carriers, they have been expired, and only leaving here immobile charge. Right, now see here, immobile charge, there are no charge carriers. So the region where, this is the region where immobile charge is present, this region is called depletion region. The region where immobile charge is present, that region is called depletion region, or space charge region, or space charge region, space charge region, or transition region. It can be called by different names, or transition region, or transition region. By default, the ideal value of this depletion region is, it is equal to 1 micron. Please do remember, it's very important. The distance of this depletion region is nothing but it is equal to 1 micron. 1 micron means it is equal to 1 into 10 power minus 6 meters. 1 into 10 power 6 minus 6 meters. That is said to be 1 micron. And the complete width of this PN junction from this point to this point, the complete width, ideally it is equal to How much means 0.5 centimeters. The complete width of PN, P-type and N-type semiconductor combination is equal to 0.5 centimeters. Please do remember this one. The ideal width of PN junction is 0.5 centimeters and the width of depletion region is 1 micron. It's equal to 1 into 10 power minus 6 meters. Right? And the region where immobile charge is present is called depletion region or space charge region or transition region. Now, these are very important for competitive exams. Now, certain characteristics comes into existence here because I am taking a junction here, which is the center point between P-type and N-type semiconductor. At this junction, there arises certain characteristics. The first characteristic is called charge density. The first characteristic is called charge density. See, this is distance x. I am considering this x-axis as distance x, and this is called junction 0, x is equal to 0. Right? And this is called depletion region. I am drawing this depletion region also. Please do remember, these are very important points. Depletion region. This one is also a depletion region. This is also a depletion region. Now, first point is charge density. First point is charge density. It is given by rho. So, what is charge density? Curve for this P-type and N-type semiconductor. See, here complete plus will be there. If you add all those, you get a complete positive charge like this. This is complete positive charge, positive charge, positive charge, positive charge. And if you say this negative, this is complete a negative. Negative, 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 negative. Right? This is called charge density. And this charge density is given by a mathematical equation called Poisson's equation. Very important. Poisson's equation. It is called Poisson's equation, and it is given by d square v by dx square. D square v by dx square is equal to minus rho by epsilon. D square v by dx square is equal to minus rho by epsilon. That is called Poisson's equation. And this charge density is given by this Poisson's equation, which is called d square v by dx square, that is equal to minus rho by epsilon. Okay. Now, this is regarding charge density and a mathematical representation of charge density. Okay. Now, let us see the second point here, which is called electric field intensity. So, you might have already learned all this in EDCMA. Second point, let us see, this is the distance, and second characteristic is called electric field intensity. Electric field intensity. Electric field intensity. Always do remember, electric field intensity moves from P-type to N-type semiconductor, P-type to N-type in anti-clockwise direction. In anti-clockwise direction. This is very important point. In anti-clockwise direction, it will move from P-type to N-type in anti-clockwise direction. Right? Or P-type to N-type, or it will move from negative to positive charge. Negative to positive charge. It will move from negative to positive charge in anti-clockwise direction. Now tell me, and this electric field intensity is given by capital E. So what is capital E now? Tell me. It is a wave which is moving from negative to positive. Where is negative? This complete thing is called negative. This complete thing, and this complete thing is called positive. So it will take its direction here, and then it will move in anti-clockwise direction, reach here at x is equal to 0 maximum electric field intensity, then again it goes like this. So it is traveling from negative to positive or P-type to N-type in anti-clockwise direction. So this is called electric field intensity. And most important point is electric field intensity is maximum at a distance at what point means at near the junction. Electric field intensity is maximum near the junction. Very important point. Electric field intensity is maximum near the junction at x is equal to 0. at x is equal to 0, right? This is distance x. So this is electric field intensity E. Now, how to obtain electric field intensity from first curve? How to obtain electric field intensity from first curve? We have d square V by dx square from first curve is equal to minus rho by epsilon. Integrate this one. Integrate with respect to dx. What do you get if you integrate it? That is equal to integration of d square V by dx square is equal to dv by dx. That is equal to minus integral rho by epsilon into dx. Rho by epsilon into dx. So what is dv by dx? I told you already. dv is nothing but voltage, dx is nothing but distance. So it is equal to electric field intensity E. So E is equal to minus integration rho by epsilon into dx. So this is electric field intensity E. The formula for second case, which is called electric field intensity E. Right? Next, third case. Third case. Potential energy barrier for holes. Energy barrier for holes or potential energy barrier for holes. Energy barrier for holes. Tell me, what is the energy barrier for holes? I told you just now, if this is the distance x, here a hole, this hole, if it is a hole, it crosses the junction, it moves towards the junction, but it will not cross the junction because complete thing here it is a positive charge. This positive charge repels this positive charge hole and therefore it moves towards to original position. So likewise, if this hole, suppose this is the first hole, if this hole wants to cross this junction, what energy it should require? It should overcome this complete energy present near the junction or depletion region. This complete energy it should overcome. This complete energy it should overcome, right? But if it wants to overcome, we need to give some external energy. But here we are not giving an external energy. That's what it is called as open circuit PN junction. This complete thing is called open circuit PN junction. This complete thing is called open circuit PN junction. Open circuit PN junction. Because we are not biasing this one, right? Now can you tell me what is the potential energy barrier for this holes? This complete thing what I rounded off, it is called as a barrier, right? So if a hole wants to move from left side to right side, it has to overcome this energy barrier. So what is that amount of energy barrier means? That amount of energy barrier is very maximum. It is up to this point. It is up to this point, and as it goes like this, it decreases towards this point. So this complete thing is called potential energy barrier for holes. This is given by V naught. V naught is called the height of depletion region or potential energy barrier for holes, isn't it? Potential energy barrier for holes. See here, some curve is drawing and it is going into p-type semiconductor because some holes are also present in this p-type semiconductor, which is a positive charge. That's what that positive charge is very minimum here. So that's what it is going crossing this junction and it is going into p-type semiconductor. Right? Next. This is called as V naught. And it's called as V naught. Next. How do you obtain V naught? Can you tell me? This is E. We know that E is equal to how much? E is equal to, just now we have written E is equal to dV by dx. How to obtain V? This is called potential energy barrier V. How to obtain that V? Anyone tell me? Anyone? Hello? Hello? Students? Dear students, are you present? Hello? For D6? Sri Charan,
Sir,
for this is
apply integration.
yes, apply integration here. If you apply integration, what will happen, Amma? Apply integration to both sides. What do you get?
Yes,
What do you get?
integral E
Integral dv.
dx is
Integral dv is v, that is equal to integration e into dx.
yes, sir.
E into dx. Very good. Right. So this is the formula for potential energy barrier for holes. Similarly, the last case, fourth one. Tell me what is potential energy barrier for electrons? Potential energy barrier for electrons. Energy barrier for electrons. Potential energy barrier for electrons. Can you tell me anyone? This is the origin, which is called distance x. Right. This is at x is equal to 0. If electron wants to move, see these are electrons. These are electrons. If electron, it moves over here near the junction, but it will not cross the junction. Why it will not cross the junction? Because it is overcome by barrier here. It is overcome by a barrier in p-type semiconductor. What is this barrier? This barrier is called negative barrier. This barrier is called negative barrier. A huge negative barrier is present in depletion region which overcomes the cross of electrons from n-type to p-type. So electron has to acquire more energy externally so that these electrons, they will overflow through this barrier and they will reach p-type semiconductor. They will reach a p-type semiconductor, and in turn current is flown in the device. So therefore, in order to overcome this barrier, electron has to acquire energy, right? What is this amount of barrier? Means this, if you add all this negative signs, you will get an amount of barrier. So what is that barrier? So this is, since it is a negative charge, so therefore we have to represent in below this x is equal to 0. So I am representing this negative. If you add complete negative, you will get like this. You will get like this. So this is what called as potential energy barrier for electrons. And from this point to this point, the height is said to be called E naught. The height is said to be called E naught. E naught is called potential energy barrier for electrons, and V naught is called potential energy barrier for holes. The relation between V naught and E naught. The relation between V naught and E naught is V naught is equal to E naught divided by anyone? What is relation between V naught and E naught? V naught is equal to E naught divided by E charge. V naught is equal to E naught divided by E, which is called charge. Or you can write this one as V naught is equal to E naught divided by Q, which is called charge. Q is also called charge and E is also called as charge. Right? So these are very important topics, Amma. Please put a concentration over here so that you will be gaining knowledge over here. Therefore, you can even score good marks in every competitive exams. Right? Next, please take down all these figures, Amma. Before that, I'll give one gate question. Get question. The question is like this. Question is like this. Please take this question. What is the shape of electric flux lines if this is N-type semiconductor and this is P-type semiconductor? A. Shape of the flux lines. This is A. B. B. C. D. Tell me what is the answer? Electric field intensity. What is electric field intensity E for this figure? This is a 2018 GATE question mark. What is electric field intensity? The shape of electric field intensity for a diode is like this. Answer? Anyone? Anyone? What is the answer? Is it A or B or C or D? Just now I told you. Just now I have explained. Electric flux lines, electric field intensity E. Electric flux lines moves from negative to positive in anti-clockwise direction. In anti-clockwise direction. Kada? Now tell me. This is N-type semiconductor. This is N-type semiconductor means majority charge carriers are what? Electrons. Electrons. What ions are present here? Donor ion, electron. Donor ion, electron. In depletion region, what is the charge? Plus. 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 And here, what is the depletion region? It is contained by immobile charge negative ion. So therefore, electric flux lines moves always from negative to positive. Negative to positive in anti-clockwise direction. So what is the anti-clockwise direction? It is moving from negative to positive. Negative is this one and positive this is anti-clockwise direction. This is anti-clockwise direction. The answer is D. The answer is D. Okay. The answer is D. Next. Let us go with energy band structure. Energy band structure of PN junction. What is the energy band structure of PN junction? And this energy band structure is like this. Like this. Please see this one, energy band structure. This is a P-type P region and this is N-type N region. In between P and N, depletion region will be present. So we have already discussed there are some certain energies called conduction band and valency band in a P-type semiconductor. In N-type semiconductor also there is a conduction band and there is a valency band. Now see here. Actually, where does Fermi level lies in an intrinsic semiconductor? Please do remember, in an intrinsic semiconductor, we have already derived in an intrinsic semiconductor. Where does Fermi level lies, ma? Hello?
Center of conduction and valency band.
Very good. Center of conduction band and valency band. So therefore, it is equal to EF is equal to, we have proved it, EC plus EV divided by 2. EC plus EV divided by 2. See here, this is a dotted line where Fermi level lies for intrinsic semiconductor. But is it intrinsic or doped semiconductor, ma? It is a doped semiconductor because P-type semiconductor means it is a doped with the P-type impurities. N-type means it is doped with the N-type impurities. So therefore, where does Fermi level lies for extrinsic semiconductors? This one also we have drawn the figures. In extrinsic semiconductor, Fermi level for P-type, Fermi level is nearer to what? Fermi level is nearer to valency band or conduction band? Fermi level is nearer to valency band. Very good. For N-type semiconductor, Fermi level is nearer to conduction band. See this figure. This is the Fermi level. Fermi level is shifting from this point to this point. Fermi level is shifting from this point to this point and it is nearer to valency band. But this is regarding P-type semiconductor. If you draw a line like this, this left side is completely P-type semiconductor and towards right side it is completely N-type semiconductor. Now see the N-type semiconductor. Where is the Fermi level? Fermi level is lying nearer to conduction band. See, this is a conduction band energy level in N-type semiconductor, so it is nearer to conduction band energy and it is farther away from valency band. Okay. Okay, so this is what called as shifting of Fermi level from its original position. This one I can call this one as EF suffix I. What is EF suffix I? It is called intrinsic Fermi level. It is called intrinsic Fermi level. So intrinsic Fermi level always lies at center point. Always lies at center point. Right. This is EFI in P type. This is EFI in N type. EFI in N type, or Fermi level in N type, and this is Fermi level in intrinsic semiconductor in P types. Right. Now, most probably in this energy band structure, the questions will be coming like this. What is the shift in Fermi level? What is the shift in Fermi level in P type and N type semiconductors? They will be asking. And also, what is the energy gap EG? What is the energy gap EG? And here, if you observe here, from this point, this has been shifted, right? From this point to this point, Fermi level has been shifted. So the gap from this point to this point is called E naught. The gap is called as E naught. E naught. E naught, just now we have studied. What is E naught? It is called a potential energy barrier. Potential energy barrier, or it is also called shift in energy levels. E naught is called shift in energy levels, whereas EG is called energy gap, forbidden energy gap. EG is called forbidden energy gap. We should represent all these points. If EG is called forbidden energy gap, EG is called forbidden energy gap. E naught is called shift in Fermi level. E naught is called shift in Fermi energy level. E naught is called shift in Fermi energy level, or from original position to previous position. And also we can also call the other thing as ECP minus ECN. See, ECP minus ECN, that is also called shift in energy level. See, this is ECP actually. ECP means what? Energy level in conduction band in P-type semiconductor. That is called ECP. Energy in conduction band in P-type semiconductor. So what is this one? If you draw a line, this is also called as ECP, right? So E naught is also equal to ECP minus ECN. See here, this is ECP, this line. So E naught is also the same distance, whatever from here to here, the same distance here also, from this point to this point, that is called E naught. E naught is equal to ECP minus ECN. That is also equal to, can you tell me another thing? What is the other one? Shift in energy levels. ECP minus ECN is one equation. Similarly, what is the other equation in the figure? Here we are taking ECP minus ECN. Next, what is the next equation?
EVP minus EVN.
Emma, EVP minus EVN. Very good. EVP minus EVN. That is also a good point, right? Now, another equation is also there. See, from this is the shift in energy level of Fermi energy level in P-type semiconductor. I call this one as E1. And this is also a shift in energy level from intrinsic to conduction band. I call this one as E2. This is E1 and E2. What is E naught, Amma? E naught is a combination of E1 and E2. So therefore, E naught is equal to how much? That is also equal to E1 plus E2. See, please do remember this one. You might not be studied in JNTU classes. This should be studied in GATE and competitive exams classes. See, this is E naught, which is called a shift in energy level. This E naught is also called energy band gap, forbidden energy gap, shift in Fermi energy level, E naught. This E naught, because this Fermi level is shifting from this point to this one in P-type, I am noting this one as E1. And this Fermi level shifting from this point to this point, I am noting as E2. So E naught is equal to E1 plus E2, we can call. And see, from this point to this point, it is also E naught. And from this point to this point, it is also E naught. Just now we have written equations. This is equal to EVN, right? So E naught is also equal to this ECP difference ECN, and it's also equal to EVP difference EVN, and it's also equal to E1 plus E2. So this equation, these terms are very important, ma. Please do be careful of all these terms. Okay, so E naught is also called what? Potential energy barrier for electrons. Do remember, E naught is also called potential energy barrier for electrons. We have studied in previous slide. E naught is also called potential energy barrier for electrons. And what is potential energy barrier for holes? It is equal to V naught. V naught. So there are certain derivations that exist over here. Please let us look into those derivations here. The very important derivations. We have already studied in semiconductor physics the concentration of holes in p-type semiconductor. What is the concentration of holes in p-type semiconductor? P is equal to, it is given by NV into e power minus of EC minus EF divided by KT. EC minus EF EC is P is equal to NV into e power minus of EF, sorry, this is EF because EF is greater, no, here EF is greater in p-type semiconductor, minus of EF minus EV, minus of EF minus EV divided by KT. This is for p-type semiconductor. Tell me for n-type semiconductor, what is the concentration of electrons in n-type semiconductor? N is equal to NC into e power minus of EC minus
EF
EF
divided by
divided by
KT.
KT, because
KT.
here conduction band energy level is greater than Fermi energy level. So that's what here we need to represent EC minus EF. EC minus EF. Right. Now, how do you represent in terms of intrinsic Fermi level? Can you tell me? How do you represent in terms of intrinsic Fermi level? If it is intrinsic, what happens? If it is intrinsic. What is intrinsic? Actually, concentration of electrons is equal to concentration of holes, that is equal to intrinsic concentration Ni. Right. Now, if it is intrinsic, what Fermi level exists? Intrinsic Fermi level exists. So instead of P, what can I write from this equation? Instead of P, I can write this one as Ni, because N is equal to P is equal to Ni, no. So therefore, that is equal to how much? Ni. That is equal to, instead of NV I am writing here, into e power, instead of Fermi level, what can I write, ma? For intrinsic, instead of Fermi level, what can I write? EFI, which is called intrinsic Fermi level, minus EV divided by KT. This is one equation, ma. This is one equation. Please do remember this equation. For intrinsic, we are studying. For intrinsic, N is equal to P is equal to Ni, you know already. So P I am replacing with Ni. Ni is equal to NV into e power minus of EFI minus EV divided by KT. Similarly, what about here for intrinsic? The same concentration here also, N is equal to P is equal to Ni. So instead of N, I am replacing with Ni. So Ni is equal to how much? Ni is equal to, now it is equal to Nc. What is Nc called? Effective mass of electrons in conduction band into e power minus of Ec minus, now what happens? It is equal to EFI divided by KT. EFI divided by KT. Isn't it? So this is what called as intrinsic Fermi level. Please do remember this points, Amma. It is called intrinsic Fermi levels. Okay. So if any doubt, please let me know the doubt, Amma, here itself. Okay. Now, why we are representing here Ni? Because N is equal to P is equal to Ni. No, that's what we are representing here. Okay. Now what happens? See, this Ni, which is also equal to P, and this Ni, which is also equal to N here. Okay. Now, because in order to represent Ni, we are going like this because it's an intrinsic semiconductor. Now what happens? See, what happens? No? P is equal to NV into e power minus of e power minus of, I am writing like this, e power minus of ef minus ev plus EFI plus EFI and minus EFI I am doing. Minus EFI I am doing. Divided by KT. So is there any problem? Is there any change here? See, I am writing this equation like this. P is equal to NV into e power minus of EF minus EV. The same thing I am writing this equation. The same thing minus of EF minus EV. Just I am adding and subtracting with EFI. Is there any change, Amma? No change. No change. Kada. So therefore now write it. P is equal to NV into, split into two parts, e power minus of EF minus EV, EF e power minus of EF minus EV, EF minus EV Ni. In terms of Ni, we need to obtain this one, NV into e power minus of EFI minus EV. So here what I am doing is EFI minus EV divided by KT into e power, what is the remaining thing? What will be the remaining thing? E power minus of EFI minus EV. This thing is gone. So what is the remaining thing? What will be the remaining thing? E power minus of EF minus EFI divided by KT. Now P is equal to, what is this equation, Amma? NV into e power minus of EFI minus EV divided by KT. So this is the equation. So this equation can be written as Ni. That equation can be written as Ni because we have written here intrinsic concentration Ni is equal to this one. So therefore this complete thing can be written as Ni into, what is the remaining thing? E power minus of EF minus EFI divided by KT, isn't it? Now get me the expression for shift in the Fermi level, which is called EFI minus EF. Because see this in p-type semiconductor here, this is the p-type semiconductor. Originally Fermi level is here, intrinsic Fermi level EFI. Now in p-type semiconductor, because we are doping with p-type impurities, it has been shifted to valence band. So it has been formed as EF. So what is this EFI minus EF? It is called shift in Fermi energy level, which is called E1, right? Now tell me, get me the expression for EFI minus EF. So what is the expression? This one can be written as P is equal to Ni into e power minus EF minus minus of minus plus EFI divided by KT. Now what happens? Tell me. P by Ni. P divided by Ni. Apply natural logarithm. P divided by Ni. Ln of P by Ni is equal to, this E will go because natural logarithm we are applying, minus EF plus EFI divided by KT. So what is the equation from this? What equation we got? Shift in Fermi level, EFI minus EFI minus EF is equal to, cross multiplied, you get KT ln KT ln P by Ni. P by Ni. So this is the equation. Shift in Fermi level in p-type semiconductor. Shift in Fermi level in p-type semiconductor. This is the equation for shift in Fermi level. Shift in Fermi level in p-type semiconductor. Similarly, can you find for shift in Fermi level in n-type semiconductor? What will be the shift in Fermi level in n-type semiconductor, ma? Can you tell me? Shift in Fermi level in p-type is EFI minus EF. That is equal to, we have proved KT ln P by Ni. Now, can you tell me what is shift in Fermi level in n-type semiconductor? Anyone? Anyone? What is the shift in Fermi level in n-type semiconductor here? Here, what is the shift in Fermi level? Hello? Hello? Students?
EF minus EFI.
Emma? Shift in Fermi level. It has been shifted to, from which value? Intrinsic to EF. So, what is that answer? E F minus EFI. So this one we have to prove. Previously we have proved EFI minus EF. This is for p-type. Now we have to prove for EF minus EFI. Now get me the answer. What is EF minus EFI? It is shift in Fermi level for n-type semiconductor. The same thing what we have applied here. The same formulas. Can you apply it and tell me the answer? What is the final answer? What we need to do? Anyone? This n is equal to, I am writing this n is equal to here. So what is that? N is equal to, n is equal to Nc into e power minus of Ec minus Ef. So what we have to do? Subtract and addition with EFI. Subtract EFI and add EFI. Minus EFI divided by KT. Divided by KT. Get me the answer, ma? The same similar thing what we did here. The same equation. What is the equation? N is equal to Nc split into two parts. What parts we need to split? Because we need to represent this one Ni here. So e power minus of, what is the equation? Ec minus EFI. Ec minus EFI divided by KT is one equation. Divided by KT into, what is the remaining equation? Come on. E power, what remains? E power minus of Ec minus EFI we have removed. So what remains? Minus of EF minus EFI minus EFI divided by KT. Divided by KT. Now n is equal to how much? What is this complete thing can be written? It is equal to Ni into e power minus of EF minus EFI divided by KT. Get me the expression, ma? Anyone? Apply natural logarithm. Apply natural logarithm and tell me the answer. What answer you get? here minus of EC minus EFI. See here minus, if you take out common, this is plus here, this is plus, and this is plus here ma. Okay, so what answer? The answer is like this. You should get like this. What is the shift in Fermi level? EF minus EFI should be equal to KT ln n divided by Ni. N divided by Ni. EF minus EFI is equal to KT ln n divided by Ni. That one you will get the answer, right? EF minus EFI is equal to KT ln n divided by Ni. The same similar equation here. This is for P type. EFI minus EF is equal to KT ln P by Ni. But here EF minus EFI is equal to KT ln n by Ni. Right? So these are the two equations. These two equations are called shift in Fermi levels, and these are very, very important equations. Next, let us go for another derivation here by using this P and N equations. P and N equations, please. Let us derive another equation for P and N. So what is the equation? Let's prove it. These equations you need to practice, otherwise it's very difficult for you. Okay, and you need to remember all these equations. These equations are very important for us, right? Now, see, we have proved for P type shift in Fermi level. What is the shift in Fermi level for P type? EFI minus EF is equal to KT ln P divided by Ni. This is the shift in Fermi level for P type. Similarly, what is the shift in Fermi level for N type? Shift in Fermi level for N type is EF minus EFI. EF minus EFI, that is equal to KT ln n divided by Ni. Right? So these are the first equation and this is second equation. What are original equations? We have original equations as P is equal to NV into e power minus of EF minus EV divided by KT. And what is the second equation? N is equal to NC into e power minus of EC minus EF divided by KT. Now, these are for intrinsic semiconductors. Now, let us go for extrinsic semiconductors. What is extrinsic semiconductor? Doped semiconductor is called extrinsic semiconductor. According to mass action law, N into P is equal to how much? Ni square. So what is N? N is concentration of electrons and its formula is Nc into e power minus of EC minus EF divided by KT into P. P is NV into e power minus of EF minus EV divided by KT. That is equal to Ni square. Now get the equation. Get the equation for EC minus EV. Just substitute it. You get what do you get here? NC into NV into e power. Add both because it is exponential. So what do you get? Minus EC here plus EF. And what about this one? Minus EF plus EV whole divided by KT. That is equal to how much? Ni square. So therefore here EF gets cancelled. So what is the answer here? NC NV into e power NC NV into e power minus of take out minus common, you get what you get if you take out minus common, EC minus EV divided by KT, that is equal to Ni square. Now apply natural logarithm, bring this NC NV here only, you keep this NC NV here divided by Ni square, cross multiply it, bring this e power this side, what do you get? E power plus EC minus EV divided by KT. Right. Apply natural logarithm, what do you get? EC minus EV is equal to KT ln NC into NV divided by Ni square. What is EC minus EV? It is equal to what? Energy gap. Energy gap is equal to EG is equal to KT ln NC NV divided by Ni square. Please do remember this equation. This is also very important equation. EG is equal to KT ln NC NV by Ni square. Because EG is equal to how much? Where EG is equal to, you can write this one, where EG is equal to EC minus EF. Where EG is equal to, where energy gap is equal to EC minus EV. So we got EG is equal to KT ln NC NV divided by Ni square, where NC is called effective mass of electrons and NV is called effective mass of holes in valence band. Right? Now, what will be the other equation? The other equation will be like this. Okay, this is for EG, KT ln NC NV by Ni square. Now, let us go for other equation. So the following all equations are very important. All equations are. This is first, second. Actually, this is the first equation, and this is the second equation, and this one is the third equation. Shift in Fermi levels. This is fourth equation, and this is a fifth equation. What we call. Okay. Next, for a n-type semiconductor, suppose we have n is equal to NC into e power minus of EC minus EF divided by KT. This is for n is equal to. Similarly, what is for P is equal to? P is equal to NV into e power minus of EF minus EV divided by KT. Right? Suppose for n-type semiconductor, what can be written? N is equal to, it's a donor concentration. So n is replaced by ND. ND is equal to NC into e power minus of EC minus EF divided by KT. Right. Similarly, for p-type semiconductor here, for p-type, what is P? P can be replaced by what? Holes. Holes means what? Acceptors. Acceptor concentration Na. Na is equal to NV into e power minus of EF minus EV divided by KT. Right. So in terms of ND and Na we have proved. Now we can even represent energy band gap or E naught in terms of ND and Na. See how can we write E naught? E naught, I told you already, E naught is called shift in energy level. E naught, shift in energy level, or this is also called potential energy barrier of electrons. Okay, E naught is called potential energy barrier of electrons, and we have proved E naught is equal to, what is the formula? We have mentioned here. What is the formula we have mentioned? E naught is equal to, it is equal to E1 plus E2. In previous case we have mentioned E1 plus E2. But how do you write E1 and E2 in the from this energy band graph? You can check the energy band graph. E1 can be written as EG minus of ECN minus EF. ECN minus EF. Right. So because this is represented by E1 plus E2 V1. So therefore it can be is equal to EG minus of ECN minus EF minus EF. You can check this one in the band structure. EF minus EVP. EVP means P-type valence energy band. ECN means N-type conduction band energy band. EF is Fermi level, EF is Fermi level. Right. So we have these equations. These equations we have. This is the complete equation. So if you substitute all these values, ECN and EF, if you substitute it, then you get an expression like this. E naught is equal to, substitute all the values of formulas, you get E naught is equal to KT ln NA ND divided by Ni square. Na Nd divided by Ni square. The same expression, see here Nc Nv, but here Na Nd. Na is called acceptor concentration, Nd is called donor concentration. So therefore E naught is equal to KT ln Na Nd by Ni square. How do you get this ECN minus EF means? See, this is N-type semiconductor, no? So we can write this one as N is equal to Nd, Nc, e power minus of Ec is replaced by ECN because it's N-type semiconductor minus EF divided by KT. Similarly, this is an acceptor impurity P-type semiconductor. We can write as Nv is equal to e power minus of EF minus EVP. EF minus EVP because EVP is the valency energy band in P-type semiconductor. So therefore, get the expressions for EF minus EVP from this equation, ECN minus EF from this equation, and substitute it. Substitute EG value from fifth equation here. Then you get E naught is equal to KT ln Na Nd by Na square. This is called sixth equation. This is sixth equation. E naught, which is a potential energy barrier for electrons or shift in energy levels, is equal to E naught is equal to KT ln Na Nd by Ni square. Similarly, if you know E naught, potential energy barrier for electrons, we can able to calculate potential energy barrier for holes. What is the formula? E naught is equal to E naught divided by E. E naught divided by E. So what is E naught? The above equation, KT divided by E. Substitute this E naught equation here, KT ln Na Nd divided by Ni square. Right. Now what is this equation? V naught is equal to, you know already. What is KT by E or KT by Q? Anyone? What is KT by E or KT by Q?
VT.
Huh?
VT, sir.
VT, volt equivalent
Voltage.
temperature VT. Volt equivalent temperature VT ln Na Nd divided by Ni square. So this is another equation for potential energy barrier for holes. This is called seventh equation. V naught is equal to VT. VT is KT by Q ln Na Nd by Ni square. What about E naught, potential energy barrier for electrons? It's equal to E naught is equal to KT ln Na Nd by Ni square. Okay. Other two equations are very important. Again, we will call these equations like this. Let us derive those equations here, and we'll close this equations. This is seventh equation. Still two more equations are there. What is that equation means? For P-type semiconductor, for example, for P-type semiconductor, for P-type. What is for P-type semiconductor? I told you already. According to mass action law, N into P is equal to how much? Ni square. N into P is equal to Ni square. Now for P-type, N suffix P, P suffix P is equal to how much? Ni square. Okay. N suffix P is equal to Ni square divided by, what is PP? It's acceptor concentration Na. Right. Acceptor concentration Na. Now similarly for N-type semiconductor, according to mass action law, we have proved it already. What is that equation? N into P is equal to how much? Ni square. N into P is equal to Ni square. So N suffix N, P suffix N is equal to Ni square. Is equal to Ni square. So what is Pn here? Minority charge carrier concentration. It can be written as Ni square divided by Nd. Nd is a donor concentration. Right. Now using these two equations, let us represent E naught again in another way. Let us represent E naught in another way. Now tell me, anyone, can you tell me what is E naught in another form? E naught is equal to, what is E naught is equal to KT ln NA ND by NI square according to sixth equation. But E naught is equal to KT ln, okay, KT ln, what is NI square by ND here? NI square by ND. I am writing Na as it is like this from equation 6. Now in denominator, what is present? Ni square by Nd. What is Ni square by Nd? It is Pn. So E naught can be written as Kt Ln. What is Na? It is acceptor concentration in P type. So holes in P type. So it can be written as Pp divided by Pn. So this is another equation. This equation is called eighth equation. Okay, next. Can you tell me another equation? Another equation in terms of Nn and Npm. Again, the same expression E naught can be written as E naught is equal to Kt Ln. Actually, it is Na Nd by Na square from sixth equation. Na Nd by Na square. Now, what is Nd? I am keeping like that only. Nd divided by, what is Ni square divided by Na? This one. Ni square divided by Na is N suffix P. So therefore, E naught is equal to Kt Ln. Nd can be written as N suffix N. It's a donor concentration N type semiconductor. Denominator is N suffix P. So this is another equation. So these are, we are learning multiple equations. Please do remember 9th equation. Okay.